There is so much more to the materials that we use in our everyday lives than what meets the naked eye. The simplest of materials on the macroscopic level are often quite complex on the subatomic level. Sister and brother, dog and owner, husband and wife. On the macroscopic level, our life is full of bonds, some of which, of course, are stronger than others, but all of which are essential to our society. Much in the same fashion as this, there are submicroscopic bonds. These bonds are called chemical bonds, and without them we would not exist. Take water, our most precious resource. Water is essential for quenching our thirst, washing our hair, watering our plants, and feeding our pets. It's the formation of its molecule, two hydrogen atoms connected to one oxygen atom, that allows it to do all of these things. Another example of a life-sustaining resource that relies on chemical bonding is salt. Scientifically called sodium chloride, it is needed not only for flavoring our french fries, but for keeping our body in chemical balance. The properties that allow salt to do this are due to its bond of one positively charged sodium atom and one negatively charged chlorine atom. Even small things are affected by chemical bonding. The penny, for instance, relies on chemical bonding for its bronzy color and solid frame. Being an alloy made up of 5% zinc and 95% copper, the penny requires these bonds to be able to stick to different metals it consists of. Though the technicalities and intricacies of bonding may arise many questions, in the submicroscopic realm we find all of the answers. There are three types of bonds: metallic, ionic, and covalent. However, no matter what type of bond is being created, it is the valence electrons that make everything possible. Valence electrons are the electrons located in the outermost electron shell, or valence shell. As valence electrons are essential to understanding chemical bonding, it is important to be able to find the amount of valence electrons an atom has. Luckily, this process is simple. You can identify how many valence electrons an atom has by looking at what group it is located in on the periodic table. Group 1, for instance, has 1, Group 2 has 2, and so on. After Group 2, you skip over the transition metals and continue the electron count as metals. Noble gases, which are in the 18th group, and therefore have 8 electrons in their outer shell, are stable. These atoms almost never bond because there is no more space in their valence shell. A way to show how many valence electrons an atom has is by using the electron dot structure, or the Lewis dot structure. This is designed to focus on the valence electrons and to show the non-bonding pairs and the unpaired electrons. The valence electrons participate differently in each chemical bond. Covalent bonding. Atoms are held together by their attraction for shared valence electrons. This is the fundamental unit for a molecule. Covalent bonds tend to form among non-metallic elements and hydrogen and other elements that gain electrons. The unpaired valence electrons are shared between two atoms either the same or different. For example, with hydrogen and fluorine. Hydrogen shares one valence electron with fluorine, and fluorine shares one of its unpaired valence electrons with hydrogen. As a result, hydrogen has 2 valence electrons, which is all it needs to be stable, and fluorine has 8. There can be more than 2 electrons shared between 2 atoms. These are called multiple covalent bonds. O2 is a molecule consisted of a double covalent bond, bonded by 4 shared electrons. N2 is a molecule formed by a triple covalent bond, bonded by 6 shared electrons. There are rarely ever any quadruple bonds. In ionic bonding, the electric force of attraction between 2 oppositely charged ions, one positively charged ion and one negatively charged ion, attract. An ion is formed by the loss or gain of an electron in order to gain a full outer shell. If an atom loses an electron, it becomes positive. If it gains an electron, it becomes negative. You can identify the type of ion an element will form by, again, looking at the group it is in. Groups 1, 2, 13, 14, 15, 16, and 17 will form positive, 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 negative, 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 and negative ions respectively. Ionic bonds tend to form between metals and nonmetals. One example is salt, or sodium chloride. Sodium with 1 valence electron gives away to chlorine with 7 valence electrons. Sodium has a charge of 1+, and chlorine has a charge of 1-. These opposites attract and form sodium chloride, which is actually an ionic crystal. Ionic compounds usually are formed by many ions grouped together in a highly orderly 3-dimensional structure. Sodium chloride has a cubic crystalline structure. In an ionic compound, the positive and negative charges must also balance. This helps identify the chemical formula. In sodium chloride, there is 1 sodium 1+ atom for every chlorine 1- atom. This becomes NaCl. However, there can be multiple charges such as calcium fluoride. The calcium ion is 2+, while the fluorine atom is 1-. Therefore, there have to be 2 fluorine atoms for every calcium atom. There is a pattern that works most of the time where you take the charges of each ion in the bond and you make it the subscript for the other ion. With calcium fluoride, you can take the charge of calcium, 2+, and make it the subscript for the symbol of fluorine. Likewise, you can take the charge of fluorine, 1-, and make it the subscript for the calcium symbol. In metallic bonding, the role of electrons is kind of quirky. The valence electrons of metal atoms are weakly held by the atomic nucleus. This causes the electrons to be easily displaced, resulting in a positively charged metal ion. These displaced electrons form a fluid. This fluid pulls the metal ions together and allows for an alloy to form. An alloy is a mixture of two or more metallic elements. This fluid is what gives metals its features. It allows for metals to be readily pounded, pulled, or molded into a different shape, or malleable and ductile. Metals conduct heat and electricity so well because of the mobility of the electrons. Also, metals are opaque because the vibrating electrons easily reflect light. Just like clothing trends help struggling, introverted children through the social challenges of middle school, periodic trends help one navigate through and work with the periodic table more easily. One trend that affects bonding is electronegativity. Electronegativity is a term to describe how strongly an atom is able to tug on bonding electrons. There is a range from 0.7 to 3.98. The trend increases from bottom left to upper right. The greater the electronegativity of an atom, the greater the pull of electrons toward itself when bonded. The greater the electronegativity of an atom, the greater the pull of electrons toward itself when bonded. The electronegativity difference in a molecule leads to a dipole, or a separation of charge. Polarity is the term used to describe the effect of the difference of electronegativity in a bond. If there is a tug of war in a bond, then the side of the atom that pulls harder will be slightly negative and the other side will be slightly positive. For example, CO is polar because the oxygen atom has greater electronegativity and the electrons are concentrated more around the oxygen atom. In the electron dot diagram, polarity is shown by the sign for slightly negative and slightly positive being over its corresponding atomic symbols. Then the two shared electrons are closer to the side that pulls harder. You can even add an arrow that points toward the side that is slightly negative. If the two atoms have the same electronegativity values, meaning that they are the same element, then it is a nonpolar bond. For example, O2 and H2 and N2. In the electron dot diagram, the two bonding electrons are in the middle to indicate that there is no pull to one side or no tug of war. If there is more than one atom for another atom, you can still determine whether the molecule is polar or nonpolar. Dipoles that equal in strength with poles in opposite directions cancel each other. Therefore, the molecule as a whole is nonpolar. However, there is still a dipole within the molecule. The net result is an even distribution of electrons around the whole molecule. An example is CO2, with one carbon atom for every two oxygen atoms. In an electron dot diagram, the carbon symbol is in the middle with a double bond with one oxygen atom on one side and another double bond with another oxygen on the other side. Oxygen will pull the electrons toward itself, but since there are two right across from each other, the magnitude of the pulls cancel out, making CO2 a nonpolar molecule. The returns from the dipoles of each bond in the molecule don't cancel out. If there is a bent shape in the diagram of the bond, then it is polar. An example is H2O, two hydrogen atoms for every oxygen atom. The oxygen atom has greater electronegativity than the hydrogen atoms, and the hydrogen atoms are not directly across from each other. Therefore, the side of the oxygen atom is slightly negative, and the side of the two hydrogen atoms is slightly positive. The overall molecule is polar. So, the next time you are racing raindrops down a window, or are thinking about adding just a dash of salt, be aware of the multitude of bonds that make it all possible. In fact, be aware of the zillion more that make our universe possible.